Waalaikumsalam Doktor.
Okay. Okay, now we have how many students in here? So one is leaving the class. Okay, actually, for this course, we just have these students, 13 students, mobility student from ITS, Institute Teknologi 10, right? ITS Institute Teknologi 10. Is it?
That's Institute Teknologi 10 November.
It's Institute Teknologi 10 Surabaya, right?
November.
10 November.
10 November.
Oh, 10 November.
Yes.
Yes,
Oh,
Prof.
10. Oh, because November. Okay. Okay. So so this class become very international. Okay. We have 19 students from Civil Engineering Department, UKM, and we have 2 students from Mobility from Jeonbuk National University, Korea, and we have 13 students from Institute Teknologi 10 November, Surabaya, right? Surabaya, Indonesia. Okay. Okay. So now, actually, we have had already one class last week, 2 classes, in fact, last week, right? Last week, and we have touched on our topic on water sources and quality for our water treatment class. But since we have new members, actually the slide for my class I've already uploaded in the UKM folio, but for today's lecture I'm going to upload after the class. So before that, I would like to go through once again on the overview of the course, because we have very quick overview of the course, because we have about 15 new students in our class. So actually this class should be in mixed mode, because actually we are required to meet physically 4 times during the course. But last time, because this class is tentatively, we have only 20 packs. So I would like to go and visit the class, the new room, because it's at the new building. So I don't know how big the room is, because now we have to accommodate around 34 students. 34 students. So I will let you know. Hopefully we can meet maybe physically a few times after the Hari Raya or Idul Fitri break. Okay, I'll just go through the overview of the course once again, so that the new friends that we have in our class know about what is going to be expected in our lecture. Okay. Okay, course overview. Students, can you see the course overview?
Yes, Prof.
Okay.
Yes, Prof.
Okay, so this slide will be uploaded also in the UKM folio, but I would like to stress a few things, a few changes that has been made because of the new numbers of students that we have in this class. So this is the water treatment and this is the course outline. I'm Dr. Fatihah Suja from Civil Engineering Program, and this is my email, and this is my room number. So you also know my handphone number, and and my office is at the new engineering building, level 3. Level 3. Okay. Okay, do I have any question? Pardon me? Okay. Okay, so I get echoed. Okay, the synopsis. Why? Do you hear the echo, or it's okay for you from your part? Is my voice clear? Students, is my voice clear?
No, Prof.
Huh? Not
Yes,
clear.
Prof.
Okay, Prof.
Okay.
Not
Clear now, Prof.
Okay, so this is the synopsis once again. So it is about covering the fundamentals that are necessary to understand water qualities and criteria, and what process units are required for water treatment. So the quality criteria we have discussed last week. So the water sources for water treatment include surface water, groundwater, and lake water. And actually this is also surface water. So we are going to look at the chemical, physical, and biological processes involved in water treatment. So basically, these are the learning outcomes, ability to apply knowledge of physics, chemistry, microbiology, and fluid mechanics to perform engineering analysis and design calculation for water treatment systems. Ability to clarify the water quality criteria for different water sources and usage purposes, ability to propose a water treatment process for various water sources and usage based on the fundamentals of the operation units, and ability to design basic treatment processes applying the concept of water treatment principles. Okay, so this teaching plan, detailed teaching plan, weekly teaching plan. So actually for week 1, water sources and water quality, we have already had this discussion on this topic, and I've already uploaded the slide in your UKM folio. And on the second week, last week actually, the regulation and standards. This one I'll cover a bit today. And this week we should be looking on the first treatment process, sand filtration. Okay, so this is the third week, and then we have coagulation and flocculation process and project presentation 1, and then we have this week, the 6th week, because our class is on Monday and Tuesday, and the Eid Fitri is going to be on that days. So this is basically it's a we won't have class this week. And then on the 7th week, on water softening and absorption process, we'll cover, and then we have mid-sem break, we have water softening and absorption process again, water disinfection, and we have membrane filtration, and we have biological treatment, and final project presentation. And then we have final project submission 1 week later, and then we have the revision week on our 14th week. And these are the references if you want to refer more, if you want to have to read more about the topic. Okay, so modes of delivery, 3 hours per week. So your attendance should be more than 80% to sit for the exam. And our class is on Monday and Tuesday from 12 to 2, and Tuesday from 9 to 10, 1 hour. So the assignment and quizzes, actually, if I can finish the topic for that week on my first on Monday, I will give you quizzes on Tuesday. If I cannot finish the topics, then I will only give you assignment. So it will carry 5 to 10% of towards your total marks. And then the water treatment design project, and this is very important, 30 to 50%, and then you have your final exam 3 hours, which cover all parts that you will be learning in this course. It is 30 to 70%. Okay, so this is what the project is about. So every group, 2 students for each group. I will ask you to this is the sample of water quality characteristic of Ganga River. So what you need to do is, these are the physical parameters, chemical parameters, and biological parameters that you always look for when you are talking about water sources for your potable water. So what I want each group to do is you need to choose 3 parameters. 3 parameters from your reference of water quality characteristic, source water quality characteristic that are not meeting the guidelines, the guideline for drinking water. So I want you to choose that location and to treat the water for the community at that location. So you need to first go to find any references on the water quality characteristics of surface water or groundwater, and then you decide that you want to treat the then you need to name at least 3 parameters that are above the guideline of drinking water characteristic, and then you choose that place to choose the location there, and then you need to know the demand, water quality demand of that community, and then you build your water treatment plant. You choose the type of unit operations that need to be included for the to treat the water quality based on your chosen water quality characteristic. Okay. So this is the water treatment plant design project. So you have to evaluate the water demand of certain community, identify specific source for water supply, explain the quality of the source, and compare it with that of the standards. Choose at least 3 parameters, but you can have more than 3 that exceed the guideline of the potable water regulation. So this is the oral presentation 1. This is going to be 3rd week of your 4th week of your course, because this is a very short presentation. You just need to make sure that you answer all these bullets points here. Okay, and then with the obtained characteristic of water, design a drinking water treatment plant that will ensure safe water intake. So prepare the process flow diagram, perform the mass balance for the whole treatment plant, and determine the characteristic of the treated effluent and compare with drinking water standards. You can use Malaysia. Actually, it's okay if you choose your country, but for those from Korea or Indonesia, but because this group, I will try to mix students, so that you know each other. So there will be 2 countries at least for each group. Show the detailed calculation of each unit operation involved in the proposed treatment plan, and then prepare then you have to make your final oral presentation, and you have to prepare your report. Prepare a complete report starting with the background of the source water, the design, and the treated effluent. Okay, so this is the proposed contents for your water treatment plant design project. There will be a section on abstract. Chapter 1, Introduction, Water Demand and Sources for a Community, Water Safety Issues, Comparison with the Environmental Regulations. Chapter 2, Proposed Water Treatment System. Chapter 3, Detailed Design of each unit in Water Treatment Plant. Conclusion, and also references that you have used in your report. Okay, So we have now we have one student leaving. Which one? Previously we have 20 and I saw one leaving, so we have 19 students. Just now, who's leaving the class? Shimir. Who's leaving the class? AH. Azam leaving the class. Which one? Azam.
Tak ada nama dia dalam ni.
Oh. Tak ada nama. How come he's in the group? The WhatsApp group. Oh, he's not. He hasn't actually. He did not even register for the class. Okay, so we still have 20 students from UKM, and then we have 2 students from Jenbuk National University. These are the numbers, the phone numbers, and we have 13 students from ITS, Institute Technology 10 November. We have 13 students, so altogether we have 35 students. So I just want 2 students for each group, so that you really do your work, your part, because only 2 students. So there will be 17 groups. There will be 17 groups. So these are the group that previously I formed the groups. Now randomly I put you into 17 groups, and each group 2 or only 1 groups with 3 members. Group number 15. So each group there will be 1 UKM and 1 Korea or Indonesian students. And only 2 groups, 16 and 17, we have only UKM students, because we don't have enough these mobility students. I hope that you haven't started anything from last week, the previous group, because I just want to make sure that you this is going to be an interesting class, because you will be working not only with Malaysian but with other international students, and then you get to know, maybe after you have finished your degree here, you can visit them. You can visit them in Indonesia or in Korea, and you all will be making friends and exchange of anything that benefits your career life. Okay. Okay, so this is the group. These are the group. This is the. Oh, these are the water treatment design plant group. No, this one is not. This one. Oh no. I should remove actually this slide. This slide should be removed. This slide should be removed. Okay, thank you. I think that's all for the overview, course overview. I will upload this new overview in your UKM folio. Any questions for this slide? Any questions that you want to ask?
So far, no, Prof.
So far, no. Okay, thank you. Then I will go into the not this one, not the. I will first go into the filtration, the guidelines and regulations. The guideline and regulations for water treatment. Water treatment. Okay. I will be talking about Malaysian context, but I think that there will be not much different in terms of the management of water treatment in whether in Korea or in Indonesia. Okay. Can you see the slide clearly if I just use this not the
Yes, Prof.
Yes, ma'am.
Okay.
Yes,
Okay.
Prof.
So okay. So water management in Malaysia, you know that Malaysia, we have many states, many states under Malaysia. We have 13 states under Malaysia. Previously, water management in Malaysia is under the federal constitution, whether the source, whether the catchment, the dam, the river, the water treatment plant, the distribution, all of these sections are under federal constitution. But then we amended, we amended the management where only the source under the state, So the water treatment plant, the distribution, the treatment and distribution are now under federal, under federal. Okay, just a bit history about our water management. Okay, principal role of federal and state governments. You can see that there are many many bodies that responsible for water treatment in Malaysia. On the policy matters, we have the federal government that develop holistic water policy for the country by setting policy direction. And for the water resources matters, we have the state government that manage the existing water basins, just now about the resource, with the view of protecting the quality of raw water and identifying new water basins when required. And then on the governance matters is by the National Water Resources Council to ensure coordination with the various state governments in the management of the water resources. Sometimes we have one river flowing into along two states. And then we have regulatory matters by we call it Suruhanjaya Perkhidmatan Air Negara, SPAN, to regulate the whole water industry based on the policy direction set out by the federal government. This is to promote an efficiency-driven regime. Okay, so these are the environmental bodies, and you can see that basically, we have four, talking not about the drinking water, but about all the environmental bodies that are responsible for environment-related matters. For the industrial waste, we have Department of Environment, Malaysia, and this is for the scheduled waste and also the clinical waste, the operators. And then we have domestic wastewater. The regulatory body is Department of Environment again, and the treatment operators in most of the states are Indah Water Consortium. This the operator that is taking care of our sewage. Okay, for the municipal waste, we have Jabatan Pengurusan Sistem Pepedal Negara and Kementerian Kesejahteraan Bandar Perumahan and Kerajaan Tempatan. And the treatment operators are Alam Flora, Southern Region, Northern Region. These are based on the areas in the country. And then for drinking water, we have Ministry of Health, treatment operators depending on the states. Although they are actually under federal, and the water supply, also we have a few companies that are responsible for managing the distribution. Okay, okay, in Malaysia, actually, I should be talking something about. Okay. 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 Malaysia water supply. I want to elaborate on this first because Malaysia lakes and reservoirs act as domestic, commercial, agricultural, hydroelectric, navigational, and recreational water resources. In Malaysia, actually, 98% of water comes from our rivers. Only 2% from groundwater. So what about Indonesia? How many percent come from your surface water for your water supply? Anybody knows? Anybody from Indonesia? How many percent? I just want to know whether your water resource come from the surface water or from the groundwater as a water source, because these are the two main class that we always talk about when we are talking about the water resource. Any Indonesian friends? How many percent from surface water? Are you all from a fourth year or third year students?
We're from second years.
Oh, second year. Any have you all got any course on water supply? Have you had your water supply course?
Not yet, Prof.
Not yet. Okay, so next lesson I'm going to ask you how many percent of water source in Indonesia comes from the surface water, and I want to know how many percent come from the groundwater. How about our Korean friends? How many percent from your water source come from the surface water? Minso? Are you in?
Yeah, I mean.
How many percent? What year are you in?
Pardon?
Civil engineering. You are civil engineering student, right?
Oh yeah.
What year are you in?
Sophomore.
Sophomore. Sophomore is first year, right? First year or second year?
Now second year.
Second year. Okay. So do you know how many percent of your water source come from the surface water?
I don't know.
Oh, you don't know. Okay. So next class, I'm going to ask you. Okay. 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 See you. So river waters or surface water is a very important source for our water supply. So that's why we have this regulation that we call Interim National Water Quality Standards. So we monitor our rivers because it is the main source of water supply. And the program we have sometimes in situ measurements, or we need to bring the sample to the laboratory. And the water, we have this standards on water quality index, meaning that we will classify, we will rate our rivers based on this index, water quality index. So this water quality index are only based on 6 parameters, dissolved oxygen, biochemical oxygen demand, chemical oxygen demand, ammoniacal nitrogen, and suspended solids, and also pH. So those of you who have taken wastewater treatment plants, so the wastewater treatment course, they are very familiar with all these parameters. Those of you who are still in your sophomore or your second year, then I expect you to know about these parameters when you have your courses on any environmental subjects, because these are the important parameters. And you can also read the notes on sources and water quality criteria for this water treatment course that I've already uploaded in your UKM folio. Okay, so in Malaysia we have this Interim National Quality Standards, where we have the WQI, the Water Quality Index, that rate the rivers into class 1, class 2A, class 2B, class 3, class 4, class 5. Okay, so if the river is in class 1, sorry, this is very the river that class means that the standard for the river water quality, it's practically there will be no treatment necessary, meaning that the river can be used for water supply without any treatment. So usually this is also, we call this class for fishery 1, meaning that this is for to have fishery with very sensitive aquatic species. For example, what? Lobster. Lobster, they need very clean water. So then they need to be in class 1. The river need to be in class 1 so that they can be used for these two purposes. Okay. Class 2A, water supply 2, conventional treatment required. Usually in Malaysia, we take our water source from the rivers, those with class 2A, meaning that we only use conventional treatment. That's why in this class, we are not going to go into the treatment units that are only used for conventional treatment, because conventional treatment are very simple. They use because they have already controlled the water source. They control the water source from class 2A, meaning that it's already very clean water source, and they just need to use a few treatment. That's why if there's any contamination to these rivers, they stop the treatment operation. They stop the treatment operation because we want to make sure that Malaysian enjoy low water tariff, because we don't want the higher technology, the more complicated technology used in water treatment plant, consumers will have to bear the cost of this treatment. That's why we control the source. And then fishery 2 also, class 2A can be used for fishery 2 sensitive aquatic species. This one very sensitive, this one sensitive aquatic species. Class 2B, they can be used for recreational use with body contact. So they are the parameters, the values that are indicative of all these class. Class 3, if they want to use for water supply, then extensive treatment required. And then fishery 3, common of economic value and tolerant species livestock drinking. So this when we have this class 3, then we understand that if we need to use it to use the river water for water supply, then we need to have more treatment units compared to the conventional treatment. Okay, class 4, usually we can use for irrigation, meaning that if you have class 4 rivers, then you don't need to treat if you just want to use the water for irrigation. And class 5, none of the above, meaning that it is very polluted and you cannot use the river water for any of these these activities. Okay, so this is what we have in conventional surface water treatment. Meaning that if it is in class 2A, then this is the conventional treatment that we use. We use screening, and then we use coagulation, flocculation, sedimentation, filtration, disinfection, and then storage, and then distribution. Okay, that's why we need to really control our surface water in Malaysia, because these are the conventional surface water treatment that being applied in most of our water treatment plant. Okay, these are the value for class 1, 2, 3, 4, 5. These are the value for water quality index. So meaning that for class 1, the BOD must be less than 1, COD must be less than 10, ammoniacal nitrogen must be less than 0.1, DO must be greater than 7. You learn from last week about the water quality from 8 to 9, meaning that the water is very clean. the dissolved oxygen. So indicative, if you go to the river, that can be the first parameter that you can study, that you can measure to know whether the river is very clean or not. You can use the dissolved oxygen probes and you see if it is 8 to 9, usually the very clean river. Okay, so the DO must be greater than 7, pH greater than 7, SS less than 25 milligram per liter, then you get WQI index of greater than 92.7. So this is the class 1 water. Okay, so this one follows. You can read through number 2, 3, 4, and 5. Okay. Okay, and then these are all the other parameters. These are the parameters that are used for determining the water quality index, meaning that to calculate the index to classify the rivers. But here you have these parameters for all the class, but these are more thorough, meaning that these are the this is not for calculation of water quality index, but for you to know which class your river water is. Okay. Okay, this one. Okay, so I just want to inform about our water rivers, water that comes from rivers. Usually in Malaysia, they are threatened by both point and non-point sources. So point sources could be from sewage treatment plant, like in Malaysia. Just now I told you that IWK is the main operator, and they operate about if I'm not mistaken, 8,000 something or 6,000 something of treatment plants. So can you imagine if these sewage treatment plants, if they are not fully treated, they are not meeting the discharge standard, then because it is the quantity, the amount of discharge water is a lot, so it will really affect our river water. Okay, so the agro industry manufacturing of sulfur or grey water from commercial and residential premises and pig farms. Non-point source could be from land use changes, and polluted runoff from agricultural areas that drain into a river, because you use pesticide for your farm. Okay, so for Malaysia, we have all rivers in Malaysia are regularly monitored by the Malaysian Department of Environment. So the National Monitoring Network was established in 1978. So from the water quality data, we use those data to determine the water quality status, whether they are clean, slightly polluted, or polluted. And then if we want to use that river, we also can rely on the class of the river that is given to the river, classify the rivers in class 1, 2, 3, 4, or 5 based on water quality index. And also you can also look at detailed parameter of national water quality standards just now. Okay, so this is the data for what Malaysia Environment Quality Report 2017. This is the latest that I can get for the analysis, the data that have been analyzed. I think we also have other, every year actually, we have this report, but this one that they have analyzed thoroughly, so I can use the data. So can you imagine in 2008, we have 579 rivers. And then in 2017, we only have 477 rivers. Could be due to eutrophication or maybe sedimentation that have make our rivers not rivers anymore, meaning there's no more water in the river and we cannot call them river anymore. So we have vanished the rivers. Okay, so from the total of 477 rivers that were monitored in 2017, 46% are classified as clean, 43% slightly polluted, and 11% polluted. So these are based on the classification of the parameters. Okay, so just to from this analysis, actually most of the quality of rivers in Malaysia were in class 2 and class 3, meaning that most of the, if you want to take this water for our water supply source, then they must be treated based on the conventional treatment or extensive treatment. Even ongoing monitoring is conducted on water quality in Malaysia. However, the improvement in the river water quality did not increase significantly. Okay, this means that you have to really take care of your river, because once it gets polluted, it's very difficult to get to improve back the water quality. You remember the lesson on water quality source that we had last week. So this improvement on the river water quality, not only about the pollution that goes into the river, but also about the retention time. Okay, meaning that if that river is big, the hydraulic retention time of the river is also HRT is also small, right? Small, B over Q. Big, meaning that you need to have a long time the recycle to make sure that the water get improved. Is also will be taking a long time, because depends on the retention time of the river, meaning that if the river is big, then it will take more time. You do a lot of effort to improve the water quality back from the class, any class to a better class. But we have example like in Perak, Sungai Nyot, in 2016 it is in class 2, but it get improved to class 1 in 2017. But not many this occurrence improvement that we can make. But in Perak, Sungai Jana, class 2 in 2016 become class 1 in 2016 became class 2 in 2017. And in Melaka, Sungai Tukang Batu, for example, from class 4 in 2016 become class 5 in 2017. So you can see that the report said that the major pollution to the 52 rivers are related to anthropogenic activities, meaning that human-made activities. So like industrial areas, sewage, workshop, residential areas, animal husbandry activities, example, pig farm, agricultural activities, landfill, plantation activities, market, food court, and hawker stalls. So cause elevated concentrations of heavy metals, mercury, coliforms, and nutrient load. So the report released by DOE in 2018 was almost identical, meaning that these are the source of pollution that you really have to look at. A total of 653 tons of BOD pollution load, meaning the organic pollution load. 835 tons of suspended solid load due to sedimentation, and ammoniacal nitrogen were released in 2018. Then you can look at this bar chart. So for the BOD meaning organic load. The organic load, the most is from the sewage treatment plant, 242 tons per day, because due to sewage treatment plant, because not many sewage treatment plants fully treat all the parameters before they get discharged to the water bodies, but some are partially treated. So you need to really, this water treatment waste water design become a very important subject actually, because sometimes because we do not know how to really control the treatment unit operation until we cannot treat all the organic load coming from sewage before they get discharged to our water body. Sewage treatment plant, and then piggery. Piggery, because they produce a very high load of organic waste, piggery, and then we can see that agricultural based industries, manufacturing industry, and also wet market. Suspended solid also from the piggery, sewage treatment plant, agricultural based industry, and also manufacturing industries. Ammoniacal nitrogen, okay. I think those of you who have taken waste and control treatment plant to make sure that you remove ammonia in your unit operation, in your biological unit operation, because ammoniacal nitrogen actually can also be removed using biological, usually in wastewater treatment plant, you use activated sludge system, but you have to really control some parameters to ensure that this ammoniacal nitrogen is removed. You can see that piggery produce a very high amount of ammoniacal nitrogen to our that make our rivers get polluted. So when plant also concentration from the sewage treatment plant is not that very high, but because we have the amount of water get treated using this sewage treatment plant is a lot, because it's every population produce how many liters per day of sewage. So the ammoniacal nitrogen also is the quantity of nitrogen discharged to our rivers is also very high. And also the agricultural based industry and also the manufacturing industry. Okay. So you can see here, this is the river water quality status in 2017. You can see that it's very difficult to make sure that the clean to ensure that the clean rivers are clean. 04 area, 204 areas, and about nearly 400,000 residents in Petaling, Hulu Langat, and Kuala Langat and Sepang. And in 2019 also, we remember that this Water Management Authority, they detected diesel oil spill resulting from sand mining activities, and we have water disruption again because the water treatment plant for Sungai Selangor, phase 1, 2, and 3 need to be stopped because of this pollution. Because as I mentioned, that we need to make sure our source water is from class 2A, because otherwise our water treatment plant, our conventional water treatment plant won't be able to produce the water quality standards that we need before distribution to the communities. And then in 2019, we can also still remember that DOE, they inspected 46 factories in Nilai that dump this, I think, dump the chemicals. So the operation of the water treatment plant also need to be stopped, and infecting 360 areas and also almost 350,000 people in Petaling, Hulu Langat, Kuala Lumpur, and Sepang. And also in 2019 also, I think all Malaysians remembered this about Sungai Kim Kim in Pasir Gudang, Johor, because we have this illegal chemical dumping. So this is a very bad situation we had in 2019 because these chemicals, firstly because they dump these chemicals into the rivers. So the rivers, so they started with polluting the river and then the air. So we have these toxic gases, such as acrylonitrile, xylene, methane, and toluene get emitted, and at that time it infected almost 6,000 people. About nearly 3,000 people were hospitalized. 111 schools and 92 kindergartens and nurseries were closed. I think all of you remember the Sungai Kim Kim case that we had in 2009, just before the, I think before the pandemic. Okay, and also in Penang also, which is highly industrialized, but we had many rivers get polluted. One of them is Sungai Tengah Nibong Tebal. We have this pitch black water with a thick layer oil on the surface. So these are the resultant of effluent discharge from nearby farms and factories. And also in Penang, Sungai Dipang, Sungai Kepar, and Sungai Rias were polluted by waste disposal due to mining activity in the upstream area. So the river become very turbid. Because before this, it's actually this is where we get, not here, I think in Penang and Perak. Before that is for the fishermen. We have this wet food octopus and mantine prawn, which are something that we are proud of in Kedah and Perak. But after this pollution of the river, the species disappear. And also we have in Perak also we have many rivers. For example, Sungai Ranjit Hitam in Manjung, which was classed under class 4 rivers. So meaning that these are if for class 4 rivers, meaning that we cannot use the river for water treatment purposes. So when you read the literatures, try to find the water quality characteristics, and then you want to treat for water supply, then you can also look at our table of class. So meaning that you have to make sure that whatever you have, it must be in class 2 or class 3, so that you can treat the water source for water supply, meaning that they can go to water treatment. Okay, the second important source, about 2% in Malaysia, we have groundwater. So in Malaysia, groundwater is monitored by Department of Environment. So we need to analyze many parameters. Many parameters based on the so we use our national guidelines for drinking water quality as a benchmark to ensure that this groundwater before they're being used, what are the treatment needed. So the benchmark is based on the national guidelines for drinking water quality. So these are the drinking water quality standard by the Ministry of Health Malaysia. Okay, so when you choose the rivers or the groundwater for your water treatment plant design, then you have to look at this drinking water quality standards. So if they are higher than the Malaysian standard here, meaning that you need to treat the groundwater from the source. Okay, so these are the drinking water quality standard parameters that you need to refer. I think that's all for the guideline. So any question from any of you? Any question? Students?
Not yet, ma'am.
Okay, good. Okay, so today we will look at the first unit operation for water treatment plant. I think maybe do you need a 5-minute breaks or you want to continue?
5 minute break is okay, Prof.
Okay, so I give you 5-minute break. So we'll start again at 5 minutes after 12, okay? Okay.
Okay, thank you, Prof.
Okay, welcome. Okay, I share another slide. Okay. It's about water filtration. Okay, first here. Okay, this is just now. This is the simple, the conventional water treatment that we have for class 2 water, river water. So you can see that usually we have this screening, and then we have coagulation, flocculation, sedimentation, filtration, disinfection, storage, and distribution. Okay, so when I talk about water filtration as my first unit, doesn't necessarily that filtration is the first unit operation. Input in your that you need to apply for your water treatment plant. So meaning that for any types of water, you need to sit down, you need to rearrange, you need to arrange that first you need to choose. First you need to choose based on your parameters, you need to choose the type of unit operations needed. And then to clean any part, and then you have to be able to arrange which unit come first. So not necessarily the one that I talked today will be the fourth unit operation. Sometimes maybe you use this as your second or third unit operation in your water treatment plant. Okay, this is about water treatment, filtration. So I will cover these are your learning outcomes to be able to plan and design the filtration process for water treatment plant. Usually this is the extraction here, clarification, filter, disinfection, and distribution. Okay, these are the need. So usually after about 5% of suspended solids may still remain as non-settleable floc particles. Even after the sedimentation process, you have another 5% of suspended solids, and it is not allowed. It is not allowed for potable water characteristic. Because it will cause noticeable turbidity and may shield microorganisms. So you need this treatment after usually sedimentation. After you use, meaning that you choose the simple one first. Comparing the sedimentation and filtration. Sedimentation is cost you less and it is a more simple physical process. Filtration also known as physical process, but also some reaction during the filtering application. We have other reaction that not only physical types of removal. So passage of water through filtration means passage of water through a porous medium, sand, to remove remaining flocks or suspended solids. So needed for most surface waters in order to provide a second barrier against the transmission of waterborne disease. You have learned about the waterborne disease last week. So assist significantly by reducing the load on the disinfection process, increasing disinfection efficiency. Meaning that before you have this disinfection process, you want to make sure that whatever that hinders the efficiency, like the turbidity, and then we have this flock, even though it is only 5%, it will affect the disinfection process. During the passage of water through the sand media, suspended and colloidal matter are removed, chemical characteristics of water get changed, and a number of bacteria considerably reduced. Okay, so when you use your when you have your wastewater, your water characteristic, and after the sedimentation process, and then go through the filtration process, and then this is the effluent from the filtration process. In the design, you need to specify how many percent of the suspended and colloidal matter are removed, and how many percent of the chemicals, whatever that you have here, is removed by this filtration process, and how much of bacteria is removed by this filtration process. So every unit operation, you need to show the mass balance, meaning the in and also the out quantity of your polluted parameters. Okay, filtration is one of the oldest form of water treatment. The filtration process used in water treatment involves flow through a bed of granular media such as sand, anthracite, garnet, or activated carbon. So depending on the type of media that you use, you will get different results. Settled water turbidity is generally in the range from 1 to 10 NTU, with a typical value being 2 NTU. So 2 NTU is also not acceptable for potable water, because this level of turbidity interfere with the subsequent disinfection process. The turbidity must be removed. Okay, the filtration mechanism, you can see that it is a very simple process, just the incoming water going through this to maybe sometimes sand, or you have more types of media, but actually the mechanism of this filtration that occurs in your unit, there are two methods, whether they are mechanical straining, sedimentation and adsorption, biological metabolism, or electrolytic action. This is adsorption, not absorption, meaning that it only occurs on the surface of the material. Okay, this is straining. Straining, usually you have this, these are your media, and this is your suspended solids or your colloidal particles. So some particles are removed by simply screening because the particle is larger than the smallest opening. So this one we call straining. Straining causes a cake to form at the surface of the filter, This is the dominant mechanism for direct filtration. This improves the efficiency of particle removal, but also increases the head loss. So usually you have this cake layer, where we call smudge tag layer, smudge tag layer here. Okay, and the second one is in-depth filtration. First, the mechanism is the straining, because this particle is smaller than the opening of the media for your filtration. The second mechanism is flocculation, because the water passes around the granular materials, particles are brought into contact with one another. This mixing causes them to flocculate and grow larger in size. Flocculation, because they meet each other, sometimes because of the charge, they get flocculated. They become grow and larger in size. So we have this flocculation, sedimentation. The interstices between the sand and grains act as sedimentation basins, meaning that they drop. Due to gravity, they drop. So this is the sedimentation basin of the particles that you have in your influent. If the mass and diameter of the particles is large enough, it will settle through the short distance from the water to the particle. Sometimes if it is small, then it will take longer time for them to settle. So meaning that we have flocculation and also sedimentation occurring. So you understand when you look at how these suspended materials occur. If just on the surface, it is screening, but in depth, due to a combination of two small particles, we call this flocculation. Flocculation, and then if they drop and then they stop at any of the media here, then it is called sedimentation. And then we also have adsorption, because the suspended particles smaller than the voids in the filter bed settle upon the side of the sand grains. So here they get attached to here. They get attached to here. So this is what we call adsorption. The particles stick on the grain because of the physical attraction between the two particles of matter. The presence of the gelatinous coating formed on the sand grains by the previously deposited bacteria and colloidal matter. So because of this gelatinous effect, they get attached to the media, sand or gravels, whatever that you use for your filtration. So there are many ways and mechanisms on how this filtration occurs. So it is a physical process, but it is a bit complicated compared to sedimentation process. And then we have also biological metabolism, because the growth and life process of the living cell, what we call biological metabolism, because the surface layer gets coated with a film in which the bacterial activities are the highest, which feed on the organic impurities. So if you have organic impurities, we have dissolved oxygen, it is an open treatment, then you will get biofilm. Remember about biofilm that you have learned in your wastewater treatment plant. So this is where biological metabolism occurs. The bacteria converts organic impurities by a complex biochemical action into simple harmless compound. So this is a purification of water. So it is not a direct filtration. Direct filtration only straining what happened on the surface. Okay, and then we have also electrolytic action. Due to the friction between the medium and suspended solids, certain amount of dissolved and suspended matter is ionized. Suspended matter in the water is ionized, carries charge of one polarity, and the particles of sand in filter, which are also ionized, possess electrical charges of opposite polarity. So these neutralize each other. So they change the chemical character of water. So because of this ion reaction in the system, so when they get neutralized, the positive and negative ion will be combined and become neutralized. So the chemical character of water will be changed because there's a chemical reaction. Okay. And also, okay. We can, when you design, when you want to use filter, you need to specify which type of filter that you want to use. So you can see the pros and cons of using, and sometimes it's not about pros and cons only, but it's about the right treatment you need for the right characteristic of water that you have. So filter types commonly utilized in water treatment are classified on the basis of filtration rate, driving force, and direction of flow. So, filters classified by filtration rate, this is what you call slow sand filters and rapid sand filters. Okay. When you say slow sand filters, usually the rate is, the velocity is between 2.4 to 3.6 meter per hour or per day per second, whatever unit that you want to use. Or if you need to use rapid sand filters, usually it's about 100 to 150 meter per hour or per second, meter per day. So you can see that this is a very far difference on the velocity of the slow sand filter and rapid sand filter. So meaning that when you want to choose, it's about your water quantity, and also and also the suspended or colloidal materials that you want to remove from your water. So this is what we call the design rate of filtration is the loading rate. If the flow rate of water applied per unit area of the filter is the velocity of the water approaching the face of the filter, meaning on the surface. So you can use both rate of filtration based on the loading rate, meaning that cubic meter per square meter per day, meaning that you are talking about the volume of water divided by the surface water, which is the surface of your filter units per day, the rate. So this is actually they are the same. When you talk about velocity or loading rate, they are the same. But when you say it's loading rate, you are talking about the amount of quantity of water going to the surface of your filter. So the unit will be cubic meter per square meter per day. But when you are talking about the velocity, it's a meter per day. It's about the velocity of the water approaching the face of the filter. So you can see here, both units are actually the same. Okay. Slow sand filter unit. So the removal efficiency is 98 to 99% of bacteria of raw water. Okay, sometimes you said that you want to use this slow sand filter because it is very effective, but sometimes your water, the amount of water quantity is will not permit you to use slow sand filter, because we'll see about this filter more after this. Completely all suspended impurities, turbidity is reduced to 1 NTU, the odor, taste, and color from the water. Usually you use this slow sand filter when you want to remove the suspended and colloidal matter in small scale wastewater treatment plant with a capacity of 5,000 cubic meter per day, and you have turbidity less than 50 ppm or NTU, the unit. Okay, so when you have your characteristic of water, you need to not only the characteristic, but you need to know the amount of water that you want to treat. Then this is your this is the guidelines for you to choose whether you want to use maybe slow sand filtration unit or rapid sand filtration unit. So if you know that you will be using a lot of water from your surface water, then you know that this is not the type of treatment that will suit your application. The gelatinous slime. So okay, so the layer, just now we talked about the straining. So there will be gelatinous slimes form on the surface and in the upper sand layer. This layer consists of bacteria, fungi, protozoa. The layer of dead debris and microorganisms builds up on the top of the sand. So we call dirty skin. The dirty skin breaks down organic particles in the water biologically and is also very effective in straining out even very small inorganic particles from water. So this is the schematic diagram of the system. So this is the layer and this is the raw water coming in. The raw water coming in here, this is the water. This is the water, this is the supernatant water, and this is the weir. Okay, this is the smooth stack layer, where we call just now we talk about dirty skin or the outer layer. This is smooth stack layer. Maybe I don't know. Maybe this is the name of a person who started this talking about or design the sand filtration. Smooth stack layer. Smooth stack layer, and then you have this is the sand filter bed, and then you have the gravel and a system of under drains. So this is a typical diagram of slow sand filter. Okay, slow sand filter construction. This is the top layer, fine sand. So the effective size is 0.2 to 0.3 millimeter, and you have uniformity coefficient of 2 to 3. So this is the type of sand that are used for slow sand filter construction. And then you have a layer of coarse sand. Voids do not permit the fine sand to pass through it. If you have the second layer, first the top layer, fine sand, and then you have the still sand, the same media, but it is a coarse sand. Thickness of this layer may be 30 centimeter. Lowermost layer is a graded gravel size, 2 to 45 millimeter here. And then you have this under drainage. So the water get collected here by the under drainage and it pass out to the chamber layer. So this is called under drainage. Okay. Slow sand filter operation. Water is uniformly spread over a sand bed without causing any disturbances, meaning that it is you don't disturb anything. So slowly, so it cannot be at high velocity. So it needs to be the water coming in need to be slow because you don't want to disturb the layer of the sand. So it is spread over a sand bed without causing any disturbances. So average overloading rate of here. Rate of filtration is continued until the head loss reach a level. Loss of head loss is level of water above the sand bed in the outlet minus the water level in the outlet chamber. So if you look at it here, so meaning that let's say you have this equipment, this is equipment to measure the head loss. You can see that the level of water in your equipment to measure the head loss is higher than the surface of the raw water in the in the units, meaning that at the point of time, then this means that you have to stop the operation, because otherwise actually the water will not be able to go through the cake that you have on the surface layer of the system, because the cake is already thick, the thick, and then that what we call head loss has been reached. Okay. The filter media gets clogged due to the impurities, results in increases of head loss. When the loss of head reaches 60 centimeter, filtration is stopped, and about 2 to 3 centimeter from the top of bed is scraped and replaced with clean sand. The scrap sand will be used in the next scraping. Meaning after you have washed the sand, then the next scraping, you take the sand and then you continue using the sand that you have already washed. The filter can run for 6 to 8 weeks, provided that you follow the average overloading rate here. So meaning that it is for small quantity of water, you have this average overloading rate, and the filter can run for 6 to 8 weeks. Okay. If you don't understand or you need further clarification, just let me know. You can interrupt me anytime. Okay. This one. Okay, slow sand filtration is a preferred technology for customers who wish to use surface water. Usually when your water source is surface water, then then sand filtration, not only slow, I'm not talking about only slow sand filtration, but depending on the loading rate, then you need to have this sand filtration. Have no access to electrical power. Okay, slow sand filtration, you don't need any electrical power. Rapid sand, then you will have to look why you need to power the equipment. Cannot or do not wish to use chemical treatment. Okay, so if you have small amount of water that need to be filtered and you don't have any source of electrical power, then slow sand filtration is the best filtration unit. Advantages: simple to construct and supervise, suitable where sand is readily available, maybe in an island. Effective in bacterial removal, no chemical pre-treatment necessary, do not need sophisticated equipment or design. Local sand may be suitable. Disposal of sludge is easier because no chemical sludge are produced, because it's no, you don't use any chemicals, just whatever pollutant or colloids that you have in your water source, and then you scrap the top layer, you wash, and then you continue using on with different layer of sand. Okay, but the disadvantage is a large area of land is required. Remember just now the loading rate, cubic meter per square meter per day, meaning that square meter meaning the surface area that you need. A large area of land is required, unsuitable for treating highly turbid waters. Color of vegetable origin is not removed. Cleaning of large filter beds requires a large labor force if it is big. Less flexibility in operation due to seasonal variations in raw water quality. Unsuitable for treating highly turbid waters. So the parameter and the recommended level is given in this table, where the design of life for your slow sand filter is 10 to 15 years. And then the period of operation, it can run continuously 24 hours a day. The filtration rate need to be very slow because you don't want to disturb any of the grain or sand that you have. Filter bed area 5 to 200 square meter per filter, meaning that depends on the surface of the filter. If you need a large surface, meaning that you cannot have only one filter, you need to divide into a few filters because it's difficult to scrape the outer layer of your sand if you have a very large filter unit. That's why they specify that you cannot go beyond this 200 square meter of surface layer. Initial 0.8 to 0.9, minimum 0.5 to 0.6, effective size 0.15 to 0.3 for your sand, uniform coefficient less than 3, height of under drains including gravel layer and height of supernatant water minimum 1 meter. So meaning these are the recommended design parameter for your slow sand filtration. Any question about slow sand filtration? Do you understand when you want to choose this type of unit operation? Okay, if you have any question, then you can stop me anytime. Okay, then the second one is about rapid sand filter. Just now SSF, now is RSF. So the mechanism of particle removal depends primarily on adsorption and some straining. Meaning that straining is not the main method of cleaning in rapid sand filter. Because a rapid sand filter it's not very quiet because the slow sand filter you cannot disturb anything. The velocity is very low for your influence to the system. It has much greater filtration rate and the ability to clean automatically using backwashing. Meaning that let's say if you have different types of water source and then you need to filter more, then you can adjust the operation. But for slow sand filtration, it's not possible. Necessary for waters to be coagulated before they are allowed to pass through the rapid sand filter, just to make sure that they have larger particles. Proper thickness of sand bed, size of the sand grain, based on we will look at the designed parameters. Washing of filter is done by back flow of water through the sand bed. Actually, if we go and visit treatment plant, it's easier for you to see. Okay, so this is mainly going back. The filter components, you need to have a filter box, the filtration media, you need to have gravel beds, under drainage system, pipes and valve, and waste wash water collection trough. Okay. Okay. RSF based on filter materials, there are 3 types. Sometimes you use single media filters. These have one type of media, usually sand or crushed anthracite coal. You can have dual media filters. These have 2 types of media, usually crushed anthracite coal and sand. And you can also have multimedia filter. These have 3 types of media, usually crushed anthracite coal, sand, and garnet. So depending on the influent and also the resultant effluent that you want, you need to specify the type of sand filter that you will be using. Okay, so these are the main features of rapid sand filters. Effective size of sand uniformity coefficient of sand, depth of sand, filter gravel size, depth of gravel, depth of water over sand filtration, overall depth of filter, area of single filter unit. Just now it's 200 square meter, but this 100 square meter in two parts for each 50 meter, meaning that it needs to be smaller, 50 meter square. Total area of holes under drainage system, loss of head that you allow, maximum is 1.8 to 3 meter. Turbidity of filtered water after the water going through the filtration unit, it is 1 NTU. Okay, so this is rapid sand filter components with gravel and perforated pipes under drain system. So plan of manifolds and lateral. This is the central manifolds, about 40 centimeter. This is the laterals. Okay, because you need all this for backwashing. For backwashing of the system, you have all this piping. Okay, you look here, rapid sand filter operation, and okay, this one, this is the water that you have. This is the sand, gravel. Okay, this is the this is single media used, and this is the under drainage system. This is the outlet pipe. Okay, so this is a piezometer tubes. Okay, when we say that the head loss occurs, meaning that the frictional this is your the water should be here. The water here, the level of water should be here because you have the outlet pipe here. So your level of water actually should be here. Should be here. This is the outlet pipe. The level of water should be here, but you have this negative head, meaning that you has loss of head. So your loss of head is here until here. Okay, this is your water level after you wash. Actually it should be here, but you have this negative head, meaning that this is not the level, but this is the loss of head that you have experienced for your treatment unit. So head loss can be calculated using Ross equation. Here, this is the equation, and also we also have a few types of equation that can be used to calculate the head loss, depending on the very detailed or very accurate way of determining the head loss. Okay, sometimes you can just use your piezometer tubes here. You can use the piezometer tubes here. You can see whether you have experienced the head loss. That's why if you want to build your rapid sand filter or slow sand filter, always have this way of measuring based on piezometer tubes. So it's easier. It's easier for you to monitor whether you have experienced the head loss. Okay. This one. So the filter operation and control. Water typically enters the filter from top and flows down through the filter media. So this is the gravel support and the under drain. So they go through here from the filter top into the sand, or if you have a multimedia, they will go through this multimedia and finally go into the under drain system that conveys the water to the effluent pipe. That converts the water to this effluent pipe. So this is the treated water. After running for a period of time, the filter media become clogged with accumulated solids removed from the water. Okay, so you have the solids in the water. So after some time, the filter, we call that So the filter must then be cleaned or backwashed to remove accumulated solids. If you don't remove, then there will be no water coming out from the sand filter. So because the sand filter has experienced a head loss, so you need to backwash. Okay, like the slow sand filter, you don't have this filtration mechanism, but here in the rapid sand filter, you can backwash the system. Filter backwash involve closing the influent, effluent, and drain valve and opening the wash water and waste wash water valve, meaning that it get clogged. It get clogged. So you stop. You stop all the influent and effluent drain valve. You close the valve, and then you provide the wash water. The wash water that will slough this clog of the media, and then you wash the media. You wash the media, and you get the then you open the waste wash water valve to make sure that whatever water that you use to clean the media, it will go through this wash water pipe, so that all the materials that cause this media to clog will always go together with your wash water. So backwash water flows upward through the gravel bed and into the filter media. As it flows through the filter media, the bed is expanded, meaning that let's say this is your level of sand, but as you wash using the water, the level of bed become higher because you have the water and also the bed. As it flows through the filter media, the bed is expanded and the water picks up the deposited solids and carries them in the wash water trough and waste piping here. The dirty water is then treated separately to recover water for recycling, meaning that the water will then be used for wash water. Okay. As filtration continues, colloidal particles become trapped in the media and pore spaces between the media grains become smaller, that cause increased velocity of the water through the pore size, increased shear forces of the water flowing through the media, and increase the head loss of the water flowing through the media. So these things happen, and these things that indicate that the water that the treatment unit needs backwashing. The result is a decrease in filtration rate, filter performance, and efficiency because the media has already get clogged. So at this time, the filter is considered clogged. The increase of shear forces the shear forces could cause particle dislodge, known as turbidity breakthrough, or the head loss of the water flowing through the media can exceed the available head. The loss of water flowing through the media can exceed the available head. The filter should be clean when either of these conditions. Okay. When you look at this head loss, you know that you need to backwash the system, meaning that you have to clean the media from all the solids that clog the filter. Okay, so you use this very high velocity backwashing water upflow of the system. Okay, so sometimes this is determined by looking, if you have the piezometer, you can use at the level of head loss that this reactor is, that this unit has experienced. Or sometimes after running the experiment for a few times, or running even your treatment plan a few times, you will be able to know that how long that this reactor will work. Like maybe 2 days. Every 2 days, you know that head loss will occur, and you need to start your backwash system. So this is what we call, you can also use 2 days of your as a preset filtration cycle, meaning that without looking at the head loss of your a filtration unit, you can always set that the backwashing will be running every 2 days, because you have experienced that every 2 days you will get a head loss that necessitates you to wash your whatever clogs of your filter that occurs in your system. Okay, I will finish with this topic and continue tomorrow. So influent piping conveys water from sedimentation units to individual filter box, and you have effluent piping that carry all the filtered water, and each filter box has an individual effluent valve. Okay, so all this piping, they have valve, because every time you need to backwash the system, sometimes you need to close the valve, you need to reopen the valve. So each piping unit must have valve. And then you also have wash water piping, because when the system is running, you close this wash water valve. Wash water valve. But when you want to backwash the system, you open the wash water valve, because you the wash water backwash water valve, and then you open the wash water piping so that you can provide clean water for backwash operation. And with backwash water piping, after you use the backwash water, you need to discharge this wash water. So you need another piping. Okay, head loss in clean filter. Each of these equations requires an estimate of either the porosity of the bed and the relative compactness of the media. Okay, most of the equations that you use for determining the head loss in your filter, you need to have many values. The porosity of the media bed. Sometimes the porosity you can measure in the lab, or you can get from the manufacturers or the supplier for your media. And you have to estimate the parameters like size, shape, and uniformity coefficient of media, so that you can use equation. If you cannot use equation, you can also use based on your experience of running the filter. Throughout a filter run, solid particles, okay, the terminal head loss through a filter bed can be calculated by use of any of the same equations of clean filter if the porosity at the end of the filter run can be determined. Okay, so when you want to use the equation that I gave you just now, you need to know many value, and you need to estimate the value. You need to also estimate the porosity of the system after it get clogged. Sometimes before clogging, it's easy for you to determine the porosity. Maybe you can put in a beaker and then you determine the porosity of the media. But after it get clogged, then you need to determine and to estimate the porosity before you use the head loss equation. So it's easy if you have piezometric, you have this piezometric equipment attached to your sand filter, so that you can determine the head loss. Okay, and okay. You will also experience head loss in piping system, because if head loss is a head loss due to clogging, head loss due to piping system, they will add on. I think all of you who are civil engineer, you have learned how to calculate head loss in piping system based on Darcy-Weisbach equation or Hazen-Williams formula. So this is for piping system. So you need to add to the head loss due to bed. Because when you measure the head loss, actually the head loss is due to head loss in piping system and head loss due to the media, the media bed. So actually you are you are concerned about the amount of head loss due to the clogging of the media bed. That's why you need to know also head loss in piping system if it is a big treatment unit, and also it's they have lots of piping for the operation. Gravel beds, the head loss through the supporting gravel bed is calculated from equation same as that for clean filter media. So gravel bed is always there. And also under drain system usually has numerous orifices. The hydraulic characteristic of this property system vary greatly. Okay, actually if it is a big system, rapid sand filter, you need to calculate the head loss not only from the media bed but also from the piping system, the gravel bed, because you want to only initiate backwashing when you have reached certain head loss due to the media bed, meaning that due to the clogging due of particles or colloids that you have filtered based on your influent water. Okay, I think I will continue on tomorrow for these slides, and I will also, it's nearly finishing. Okay, so tomorrow we have one 1 hour for our class. So I will continue on with this slide, and also I give you a few examples on the design of sand filtration, and then maybe I give you 1 or 2 questions as your homework. Okay, students, we'll see you tomorrow. Any questions before I end the session? Any question? Any questions? Are you still there?
No, Prof.
Okay, no question. Okay, I hope that you can understand. And we'll continue on tomorrow at 9 to 10. Okay, see you tomorrow. Take care.
See you, Prof. Thank you very much.
Thank you very much.
Okay, welcome.